Well, this is the outline I'm going to be using. Of course, your program says I'm going to talk about hydrogen infrastructure, but I have a lot more information I'm going to be talking about too. Number one, I'm going to compare hydrogen infrastructure costs with the cost of electrical infrastructure for battery electric vehicles. And I'm also going to compare alternative vehicles with these four attributes. I'm going to start off by saying we agree with the Obama administration that we need to electrify the vehicle in the United States. However, to power electric vehicles, there's three options. We can have battery electric vehicles, as you all know, plug-in hybrids. And of course, the administration supports those two, but they've totally neglected or tried to kill the hydrogen-powered fuel cell vehicle program, which is another way to drive electric vehicles. In terms of plug-in hybrids, to the best of my knowledge, this was the very first plug-in hybrid electric vehicle made by a major auto company. But this happens to be a Ford fuel cell electric vehicle. But they put a bigger battery in it, so it had 25 miles all-electric range. I had the privilege of driving this around Washington, D.C. several years ago, which was quite an experience. I have two sources of data in this presentation. One are the simulation models that were referred to, put together by the National Hydrogen Association. And also I'm going to refer to data from the McKinsey & Company report on alternative vehicles in Europe. The NHA task force, these are the companies that participated in our study. It was headed by Frank Novacek of Xcel Energy, which is a large Midwestern electric utility. The McKinsey report had even more participants. In particular, they had the participation of 10 OEMs, automobile companies, the 10 major companies. And why that's important, the auto companies provided proprietary cost data to the McKinsey analysts. So when I get toward the end of my presentation and I talk about the cost estimates from McKinsey, I think they have particular credibility. In terms of hydrogen infrastructure, most of you probably know this, but almost all hydrogen today is made at a central production plant, mostly by steam methane reforming. But once you make the hydrogen, of course, you have to deliver it. And in the United States, there's three major ways. You liquefy the hydrogen, deliver it by truck, you compress it and deliver it in a tube trailer, or you build hydrogen pipelines. And all three of those transportation options are used in the United States, delivering thousands of kilograms of hydrogen to industrial users, every year. But for refueling vehicles, you can also have on-site production, either by electrolyzing water or by steam methane reforming of natural gas. In terms of steam methane reforming, you use natural gas plus water to produce hydrogen. And here's the chemical equation for that. And the reason I put this up here, I want to demonstrate that one carbon atom produces 4 hydrogen molecules. And that's important because half the hydrogen comes from the methane and half the hydrogen comes from water. So you might say that this is already 50% renewable. And of course, that's one of the reasons if you use hydrogen made from natural gas in a fuel cell electric vehicle, you cut greenhouse gas emissions by about 50%. But of course, this is where we want to go. We consider natural gas to be a transition fuel for making hydrogen. But eventually, we'd like hydrogen to be made by one of these techniques and, of course, one of these sources. And that's one of the strengths of hydrogen, like electricity, that hydrogen can be generated from a number of different sources. And for example, here's a graph or map put together by NREL showing, again, that you can produce hydrogen from wind up in the Midwest, PV in the Southwest, and biomass over the eastern part of the country. This is a chart put together by Charlie Fries at General Motors showing the hypothetical upper bounds of what you can do. For example, from biomass, you could produce enough hydrogen for 395 million cars, which is about 3 times the US car fleet. Solar, 21 billion cars, or 16 times the US car fleet. Wind, 9 times the US car fleet. And geothermal, about 2 times the US car fleet. But Charlie did not include one option that's already being used up here in Orange County, and namely that's to use the anaerobic digester gas from a wastewater treatment plant. And this station is up in Orange County. And basically they take the digester gas and run it through a molten carbonate fuel cell. And Dr. Samuelson, I see, will be talking more about that a little bit later. And they use about 75% of the energy to produce electricity to run the wastewater treatment plant, which saves them hundreds of thousands of dollars a year, and then also cuts down the carbon footprint substantially. But they use the other part of the digester gas to make about 100 kilograms per day of hydrogen, which is enough for about 160 fuel cell vehicles. So this is in operation up in Orange County. So for those of you that live in Orange County, I want you to remember, every time you flush the toilet, you're contributing to hydrogen fuel. Now, jumping clear across the country, this is the first of 9 solar hydrogen plants being installed, solar hydrogen stations being installed along the eastern seaboard by Sun Hydro. And this shows the map of where these stations will be deployed. The first one is deployed at Wallingford, Connecticut, and that's the site of the Proton Energy Systems, the electrolyzer company, which was purchased by Tom Sullivan, who's the CEO of Lumber Liquidators. And when he finishes installing all 9 of his stations, you can be able to travel all the way from Maine to Miami in a fuel cell vehicle. Now this is the device that we developed at H2Gen, a small-scale steam methane reformer. Again, takes natural gas and water and produces pure hydrogen. And these are the prices that we can produce hydrogen today, about $5.32 per kilogram. And that's assuming that natural gas is $11 per million BTU. Of course, it's much lower than that today. If you add compression and storage, which we didn't supply, the total cost we estimate is about $8.50 per kilogram, and that's equivalent to gasoline at about $3.60 per gallon of gasoline on a range equivalent basis. We also developed this unit with 5 times higher output, and then we could get down to about $2.10 per gallon of gasoline on a range equivalent basis. And a very busy chart that's in your handouts. Here's the 210 and 360 per kilogram per gallon of gasoline equivalent. And that's assuming we build just 10 units, which was about our production volume in 2009. If you go up to 200 to 500 units, we're estimating we can get the cost of hydrogen down to $1.34 to $1.86 per gallon of gasoline. So we believe that hydrogen is already cost competitive with gasoline. Now I want to bring you up to date with the status of fuel cell electric vehicles. Many of the Toyota vehicles are in the NREL Learning Demonstration Project. They've actually analyzed, they've had 155 fuel cell vehicles now in the fleet that they're analyzing. They have looked at refueling at 24 hydrogen stations, 15 of which are in California. And these cars have now traveled, they just passed the 3 million mark a couple months ago, so they've now traveled 3 million miles. And these are driven in ordinary day-to-day driving by ordinary citizens. They've refueled over 27,000 times. Again, high pressure compressed hydrogen put into the car by ordinary citizens without any major incidents. So that's kind of the status of the DOE's evaluation of on-road experience with, as I say, 155 fuel cell electric vehicles. And of course, I know Toyota's collecting those data, as we heard at lunch, for the RAV4, but we don't have those data yet on battery electrics nor plug-in electric vehicles. Here are the stations that were in the program in Southern California. 4 of these are still available now for public refueling of hydrogen vehicles, and 16 are either under construction or funding has been allocated by CEC to build 16 more stations, so there'll be a total of 20 in the Southern California area in the next few years. In terms of fuel infrastructure costs, these are the economic assumptions we used in our model. We assume the government pays for 30% of the hydrogen stations, which is the current law. Probably won't survive this week and certainly not the next couple months, but anyway, that's the current law. And we assume that industry pays the other 70%. And we made a requirement the industry that put in the 70% had to earn at least a 25% internal rate of return initially, and then dropping to 15% when the capacity factors get higher. And in terms of cost, initially we're assuming $1 million to $2 million for the fueling station, dropping to maybe $243K to $1.2 million when you get to larger scale production. For the electric charging infrastructure, we use the recommendations of the Electrification Coalition, which is a group of organizations promoting the use of plug-ins and battery electric vehicles. And they recommended that we needed 2 public outlets for each battery electric vehicle initially to overcome range anxiety with potential customers. In terms of the cost of the electric outlets, we used $2,000 to $3,000, which was the Electrification Coalition estimate. Idaho National Lab estimated about $1,800 per outlet. But when we look at reality, Coulomb Technologies is in the process, I guess, of installing 4,600 Type 2. Those are 240 volt outlets for $37 million, and that comes out to about $8,000 per outlet. Now, since I made this slide, I learned that Hawaii is putting in 250 outlets in Hawaii at a cost of $4.6 million, and that works out to $18,400 per outlet. Now, the Electrification Coalition in their roadmap requested the government spend $120 billion over 8 years to put in enough electrical charging outlets for battery electric vehicles. So these are the results from the NHA study. The green bars are the cost of hydrogen infrastructure. The red bars are the cost of the electrical infrastructure for government and for industry. And you can see the electrical infrastructure costs more. Now, these are the results from the McKinsey report that I referred to earlier, and they have even more astounding results. They estimated that to put in a hydrogen fueling infrastructure for the entire European Union would cost about 101 billion euros over 40 years. But to put in enough electrical outlets for battery electric and plug-in hybrids, they estimated it would cost 5 times as much, 540 billion euros. Now, those are the cumulative infrastructure costs. McKinsey also pointed out that in Europe, every day, every year, they spend from 50 to 60 billion euros for roads, the same for telecommunications, 50 to 60 billion also for oil and gas infrastructure. So putting in a hydrogen infrastructure is negligible compared to what's put in terms of infrastructure already. And even the batteries and the plug-in hybrid infrastructure is small compared to what is spent on other infrastructure projects in the EU.